A lot of his friends are talking to him because they not to because they felt like
Is there an outlet?
nature. No. I was seeing game last
Derek came out. It's the same thing on the cabinet, so. Oh, you can find? Okay. Thanks. Yeah.
he's just shifted. I don't want to do it right now. All I know is like the first year, he doesn't do that. He doesn't. You didn't even know that way. He's got
All right, it's 6:31 now, so we'll get started. A few people might be trickling in. There is a handout here if you want a hard copy. It's the same thing I posted to Piazza, but it has the questions we're going to be working through in like space to write the answers as we go through them. So feel free to grab one of those if you haven't already. But again, it's the same thing as what's on Piazza, so it's not necessary to have it. So today is, well, just a reminder, sorry, what? Oh yeah, it's 3 pages. I didn't staple them because that would have taken time and effort that I didn't want to do into a menial task. So it was stapling. Yeah, but just to remind you, my name is Kirsten. I'm a 4th year PhD student in the machine learning department, and I am one of the TAs. And this is the first recitation. It's a review of probability. Just fairly basic stuff. You should already know most of it, so hopefully this is just a refresher for you. But if you don't know something, this can be like kind of a diagnostic to point out what areas you should look into and make sure you have a strong background in, because a lot of these concepts are going to come into play when we're learning about actual algorithms and machine learning, and it's going to be assumed that you understand these things, so this is kind of to get you all up to speed on that. If you have more questions on anything, you can always come to my office hour, which is Fridays at 4. It's up on the 8th floor. Or anyone else's office hour. We're happy to talk about any of stuff. So my plan for today, I outlined some major topics to cover and then had practice problems for most of them. And so my plan is that we can kind of solve them together. I'll show them and then give you all a couple minutes to work on them. If someone wants to come up to the board and solve it in front of the class, then we can talk about how you went through it. Or if nobody volunteers, I can do it myself. So, all right, first of all, before we get started, are there any questions? About anything? Okay, cool. So to get started, there's a handout in the front. It's the same thing as on Piazza, so feel free to take them out. So we'll start out with a few definitions. So we're going to define, can everyone see in the front? Do I need to dim the light by the projector? Okay. Okay. I think that's as good as we're going to get, but that is better. So to start out, a lot of the ideas of probability are concerned, like say it's a situation that you have this random experiment where you have something you're doing, you expect some outcome, but you don't know what it is. There's some randomness associated with what it's going to be. So we're going to define an event A as an outcome from a random experiment. So suppose your random experiment is tossing a coin. What what kinds of events can you get from tossing a coin? Yeah, right. So the particular event would be, say, you tossed the coin and you got heads. You're going with heads. And then the sample space is the collection of all outcomes that can take on. So like you mentioned, for tossing a coin, heads and tails. And then a random variable x is a function that maps all of your outcomes to real numbers. So heads or tails, that's not a real number, so we might say, if you get a heads, we're going to count it as 1. If you get a tails, we'll count it as 0. But you can also think of defining other random variables. So suppose that you were instead tossing your coin 10 times, and your random variable is the total number of times you got heads. So then you're actually looking at a series of repeated events, and then your random variable is the total number of heads in that case. And then also, we can define a probability measure associated with events that indicates how likely that event is to happen. So if you have a fair coin, the probability that you're going to get heads is 1/2. And for a probability, there are several axioms of probability that have to be satisfied. First of all, the probability of any event occurring is at least 0. No negative probability, nothing. The probability of the entire sample space, which is all the possible outcomes, is 1. So in the case of tossing a coin, the probability you're going to get heads or tails is 1, because you're guaranteed to get at least heads or tails. No other option. And if you have 2 disjoint events, the probability that either one of them will occur is equal to the probability of the first occurring plus the probability of the second occurring. So an example like that would be, so for disjoint events, say the probability of in a coin toss getting heads or tails is disjoint. If you got a heads, you know you didn't get a tails. If you got a tails, you know you didn't get a heads. So the probability of heads or tails is the sum of the 2. But for other cases, sometimes it's possible that one thing can happen in the intersection of the 2. So again, that doesn't hold if we're not disjoint. So set operations apply to probabilities. You've probably seen all of these laws in multiple other math courses. Just commutative, you can swap the order of the events and everything still holds. Just a notational reminder, you've probably seen this again before, but so we're using this like U shape to denote union, and then this upside down U to denote intersection. So here this is A or B, which means either A or B, and then this is A and B, which means both things have to hold for it to be true. But again, just the commutative, associative, and distributive properties, and then De Morgan's law. So you've probably seen all of these things before, but and we can use these set operations to prove various identities when it comes to probabilities. So I have a few practice questions on your handout, and so I'll give you a couple minutes. You can go through and do that, and then if someone wants to volunteer to do it on the board, we can talk about how you went through the process. So maybe we'll do, I'll give you some time to do the first one, and then we'll do it together and talk about it, and then move on. So hopefully the later ones will go like faster once we've done the first one together. So I'll give you a couple minutes for that. Once you're done, just like look up, and once a good number of people are looking at me, we can talk about it. Huh? What do you mean? No, you're proving it is true or not. There's a little question mark over here. So it may or may not be true, and your goal is to show if it's true or not. Huh? Oh, prove or disprove. Yeah.
It's not this
All right, how many people are finished or almost finished? Do you need more time? Oh, raise your hand if you're finished. Okay. That area of the room seems to be a good area to sit if you want to finish, I guess. And the rest of you, are you close to being done? Or so maybe like one more minute? Then we can talk? Okay.
Which one? Why? What? It's not true. And then we can give it to them all the time. Orange. So bring a compliment to this for no reason. I use only some just to read them. I don't know.
All right, I think we can go through it together now. Does anyone want to volunteer to solve it on the board in front of everyone? Okay, come on up. What's your name?
Wait.
Sorry, what?
Wait.
Wei Peng? Okay, I'm going to try to learn everyone's names. This is a reasonable sized course, so I should be able to do it sooner rather than later. just the first one. Yeah. Right, so you got that the first set here. So first you did additive and then associative, and you saw that you got A intersected with A complement, which is the empty set. So that means that the probability of this quantity is 0, regardless of what either of the sets are. But the probability of the union of A and B is not always going to be 0. So that's right, this one was not true. Another way, I don't know if this could help other people think about these types of problems, but another way to think about it is if you draw like little diagrams and think about exactly how these probabilities intersect with each other for different groups. So depending on if you're more like a visual type person, that can help. So suppose you have this rectangle that is our sample space. So this is anything that can happen. So the probability of something being in this entire rectangle is 1 by definition, since that's our sample space. So then say that this is a collection of events, we're going to call it A. So the probability that A happens is going to be everything in this circle. Everything outside of the circle is A complement. So you can see here there's no intersection between A and A complement. Then if we were to draw like another circle to represent B, here we can see that the union is going to be everything in both of these circles. The intersection is only going to be a slice in the middle, and so then you can think about like, well, what is A but not B? It would be like this part here, this little like crescent moon. That's the way they can help you think about how different sets and complements intersect with each other. So sometimes that's easier to think about intuitively, at least for me. So now we can take a couple minutes, go through the second one. Maybe that'll go a little bit faster this time, and then someone can come up and talk about it. So again, this may or may not be true, and your goal is to see if it's true.
Yeah.
All right, just a show of hands. Who's ready to talk about number 2 now? All right, it looks like most people. Does anyone want to volunteer to come up? Do it on the board. Okay, of the people who have finished it, how many of you are confident in your answer? Okay, maybe one of you would like to come up.
Oh,
Yeah, okay, cool. What's your name?
Aditi.
Aditi?
Yeah.
All right, cool, great, thank you.
Okay, so the first thing I did was move this to this side. So and then after that, these two events are disjoint because there's a here and a complement here. So then you can write B intersect a complement or and then you can use the distributive rule here. So that's B and then B intersect AC union A is just like the whole universe, I guess. So B intersect that would just be B.
Right.
Yeah. So then you got P of B equals Q, which is true.
Yes, that's exactly right. So if you were to look at the area up here, the intersection of B with A complement is everything that's in B but not in A. So that's going to be this section. So here you can see that it's just the probability of B minus both of them together. And so you can kind of intuitively see that this is what it needs to be and then go through the operations exactly that way to formally show it. So now we have one last question like this. And so you can see that this is, remember how before in the axioms we had union for disjoint things. So now we're going to see if this holds in general, because we're not saying anything if A and B are disjoint or not. So you can see if this is true or not. And just a hint, it can help you if you use the result from 2 for this one. And we can talk about it in a minute or 2. How many people are ready now? All right, another minute.
This is the basic.
What is All right, would anyone like to solve it on the board? They're big shoes to fill, so other people can do it too. Yeah, go ahead. And what's your name? Brian? Okay. Yeah. So, do you want to talk through the steps that you did?
Okay. So we take the part from part 2 and we substitute it in, and those two areas are disjoint, so we can use the probability A and B equals probability of first plus the second for the first one, and then
Yeah, that's right. Another way to look at this is going to look at the picture would be, if you're looking at the probability of A or B, you have A right here. And then, so that's all the circle of A, and then all the circle of B, like this. And you can see that this middle part, that's in both A and B, you ended up counting it twice, because you counted it once in A, you counted it once in B, but it only needs to be in there once. So you have your probability of A, probability of B, and then because you double counted this intersection, you subtract one of them out. The next topic we're going, does anyone have any questions on that before we move on? Okay. The next topic we're going to talk about is conditional probability. So here, it's denoted by this bar, the conditional probability of A given B. That means the probability that A is going to happen, given that you already know that B happens. So B is, like, you fix it to a particular value. So it's defined as the probability of both A and B happening together, divided by the probability of B, what you're conditioning on. Again, assuming that the probability of B is greater than 0, but if the probability of B is 0, it doesn't really make sense to condition on something that didn't happen, right? So if we rearrange this definition, we can get what's called the chain rule for probabilities. So that's if you have two events occurring, you can separate it out by you choose one event that happened first. In this case, we said B. So you take the probability of B and then multiply by the probability of A given B. And you can generalize this result to any number of variables occurring together. You just have like more things together on one side or the other as you keep chaining things on. So we have an example here. So suppose we have two dice, equal probability of getting any of the 6 numbers on both dice. And so we want to find out what is the probability that the sum of the numbers that we roll on the 2 dice is greater than 6, given that one of the dice is a 3. people are ready?
No?
Yeah.
All right. Most people. How many people would like to volunteer? Okay, go ahead. What's your name?
Fletcher.
Fletcher. Okay. Come on up.
Right.
Okay, well, you don't have to. You just want to talk.
Yeah, I guess just so given that you already rolled a 3-on-1, they're two independent events, so it doesn't actually affect the other one. So basically, you need to roll a 4 or a 5 or a 6 on the other one. Or no, wait, it's greater than 6, give them 3. So yeah, a 4, 5, or a 6. So it's one half.
Yeah, that's right. There's a more complicated way of doing it where you could like list out all the different possibilities and then say, like more use the definition, but that's the better way. So sometimes there are like, that's the thing. Sometimes there'll be questions and if you do it like according to the way strictly by definition and things, you can get the answer, but sometimes it's more painful. So sometimes just having a sort of insight like that helps you get an easier answer that's going to be the same thing. But the other way you could do it is, right, there are 36 options. You get a 1 through 6 on each of the dice, and then all the possible sums you could get, and then basically like only look at the section where one of the dice is a 3, and then you'll still get the 1/2. But it's more cumbersome to do it that way. The next topic we're going to do a little quick problem on is marginalization. So if you have a joint distribution where you have multiple variables, here we're supposing you have 2, probability of x and y together, you can find the probability of, say, just x by what's called marginalizing out the other variable. So basically what you do there, you sum over all the different values that that other variable can take on over the joint, and then here if you go back to the chain rule that we learned before, this expression here, the probability of x given y times the probability of y is equal to the probability of x and y. So that's the way that you can find the probability of just x. So there are situations that arise where you only know relationships between variables that happen together, and then for some of them you know like other things, but you want to like, maybe just figure out the probability of x. So we have a little example here. I was just making up numbers for this, and I was concerned if they were accurate or not, and I learned that far more people participated in buggy than I knew. Originally, I was like an order of magnitude less than this. Actually, no. The actual number I found on the website was like over 400, and I thought that just sounds too much. I'm not going to have that. But so here, suppose that you looked at the undergraduates at CMU, counted them up by year, and then the number of people each year who are on a buggy team. And we want to find out the probability that a student chosen at random, we don't know what year they are, what's the probability that that person is going to be on a buggy team? So we can use the handy definition of marginalization right above there. Here's the element. Oh, and if you're doing it now, you don't have to like get the final number because it's not that easily calculated unless you want to do some long division yourself.
take that.
It's the same. And then this, everything will cancel it. So you need to. I did right.
Raise your hand if you're finished. Okay, move people. Does anyone want to say what you did? You can either write it on the board or just talk from your seat if you'd rather do that. Yeah, what's your name?
Emily?
Emily, okay.
Okay, so you first take the probability of being on a buggy team given freshmen, so that's like 100 over 1100. And then multiply that by the probability of being a freshman, so that's 1100 out of 3000. And then you do that for every year and add them all together.
Okay. Yeah, so I'll just write that out in case anyone better that way. So basically what you're going to do here is you want to know the probability that any person was on a buggy, which I'll say B is 1, and so you're going to sum over all possible years that that person could be the probability that they're in that year, and then the probability that they built or they participated in buggy given that they were that year. So the options, like Emily mentioned, freshman through senior, so the probability that you're a freshman is going to be 1100 out of the total of 4000. And then the probability that a freshman was on a buggy team is 100 over 1100. Or sorry, oh yeah. Oh no, wait. The probability that someone was on a buggy given they were a freshman, yeah, is and then you continue for all of the different class designations of someone to be. Just out of curiosity, was anyone here ever on a buggy team? Okay, cool. So I have a younger brother who's an undergraduate here. Who's on the robotics buggy team. So that's not they don't actually have a person in there, but they do it automatically. It seems safer that way, in my opinion. Okay, so the next thing we're going to cover is called Bayes' rule. It's really useful if you have probabilities in one form, a certain conditional probability, and you want to see how it relates to if you swap the conditional on that probability. So we can derive Bayes' rule, first of all, by looking at the definition of conditional probability. So again, just the definition of conditional probability is the probability of two events occurring divided by the probability of what you're conditioning on. And if you apply the chain rule to the probability of the intersection of A and B, you essentially get Bayes' rule, and you can see, again, this is useful because it relates the conditional probability of A given B to the probability of B given A. And if, in many cases, you don't know probability of B directly, so you can marginalize out A from the joint of P and A, which here, if you do the chain rule, you get that form. So the example problem we have here is that you're being screened for this rare disease. Only 1% of the population has it. And the screening procedure is 95% accurate. So if you have the disease, it's going to return a positive result 95% of the time. And if someone doesn't have the disease, it can still make a mistake 1% of the time, and it's going to say that a healthy person does have the disease. Unfortunately, you took this test, it said you had a positive result, but all hope is not lost. We're going to calculate the chance that you actually have this disease, given that you had a true test result, a positive test result. You want to know the probability that you have the disease. Again, you don't have to go through and like do the full calculation if you don't have a way to do it that is not your head, because that's a pain. How many people are ready? All right. Does anyone want to come up and do it on the board? Yeah. What's your name?
Brian.
Oh, okay. We have another Brian.
So you just apply the base rule, which is
Would you get C one?
I didn't do the calculation. So this one's given in the problem statement, which is just 0.95. And then this one's also given, it's 0.01.
Wait.
And then the probability that t returns positive is, you can just break it down into if it's positive given you have the disease, or if it's positive given that you don't, which is just 0.95 times 0.1 plus 0.01 times 0.99.
Right. So then if you, I don't know if you went through it, but if you want to get the actual number, it's about 49% chance that you have the disease, even though this 95% accurate test that you did. Just because so few people have it, the fact that there still is this small positive, negative, or like false positive, you're still more likely than not healthy, just because it's so rare. Okay, another topic that is important to know about is this concept of independence. So two events A and B are independent if the probability of both of them occurring together is equal to the probability, or equal to the product of the probabilities of them occurring individually. So in other words, that means that the conditional probability of B given A equals just the probability of B. And you can see that that comes in because if the probability of B equals the conditional probability of B given A, you can substitute that back into the first statement, and you basically got the chain rule, which we know is true for any combination of events. So basically what you're getting from here, if they're independent, A and B are independent, really you're not getting any extra information about B if you know A, because they're totally separate. And the concept of conditional independence is similar, but you have this other event C that you're conditioning on. You can see that just translates into the product of your probabilities of conditional probability of A given C times conditional probability of B given C. So the example here, here we have this table that we have 3 different variables, and we're showing all 8 combinations that these 3 binary variables can take on together, and just the probability. So like here, 1 out of 15 is the probability that x equals 0 and y equals 0 and z equals 0. Over here, like this 8 out of 45, that's the probability that x is 0, y is 1, and z is 1. So we have, the first question is just asking, is x independent of y? So before we get into this, do people have an idea about how to start approaching this problem? I saw a nod. All right, one indication of yes and no indications of no, so I'll let you at it for a few minutes. Are people ready to talk about it yet? Is anyone finished? Okay, one person. All right, we're almost out of time, so I'm just going to solve this one on the board together so you can see how it goes. The next one is very similar, but a little bit longer, so I think if we can get through this first one together, we'll be all right. So first, what's one thing that you can check to see if these, if x and y are independent? Yeah?
The probability of y equals 0 given x equals 0 is equal to the probability that y is equal to 0.
Yeah. So if you want to calculate the probability, we're going to see here. see if this holds. So equivalently, it could also be probability y equals 0 equals probability y equals 0 given x equals 0. So we just need to check if this holds. So we can get this from the table, the probability that x equals 0, we just sum up any of the times that x might be 0. So that's going to be this column and this column. So 1 over 15 plus 1 over 10, 4 over 15 plus 8 over 45. And that ends up being 11 over 18. And to calculate this value here, we're going to use the definition of conditional independence, which is going to be the probability that x and y are both 0, divided by the probability that y is 0. So here, the probability that x and y are 0, that's going to be x 0, y 0, and then z can be either 0 or 1. So that's going to be 1/15 plus 4/15. And then the probability that y is 0, we're just going to sum this entire row. The 1/15, 1/15, 4/15, 2/15, which is 8/15. If you add this up, it's 5/8. So here we have probability x is 0 is 11/18. Probability that x is 0 given that y is 0 is 5/8. They're not equal, so we know that they're not conditionally independent. The next example, it's similar. You just have to condition on z. So if you understand how this one works, it's just a slight extension. I think you can handle it. But if you have questions, again, my office hour is Friday, where you can talk to any of the instructors. So the final section we didn't get to, but a lot of that is kind of reference of some common distributions and definitions for probability distribution. So the goal is that this sheet can be like sort of a reference for you all to go back to when you're learning stuff or doing homework.